Awesome. Thank you for joining today. My name is Seth Markle. I'm a senior principal engineer in S3. I've been in S3 for 12 years, been at Amazon for 17. Really excited to be here today. We're going to be talking about using data analytics to improve product quality and customer satisfaction. And I'm really excited to be joined by some guest speakers from Coupang, Seshu and Aldi, who are going to come up later and talk a little bit about how Coupang uses data analytics to improve their customers' experience. So let's get started. I want to start off talking about how we build at Amazon, specifically in the context of S3, but what I talk about here is pretty universal. I'm sure most of you know S3 is a really large-scale storage service. S3 is comprised of over 235 microservices. We house over 280 trillion objects, and we average around 100 million requests per second. Really large-scale service. Part of S3 we consider the request path. The request path is the portion of S3 that's responsible for actually participating in your get and put requests. And that's a much smaller set of services than the entirety of S3. The request path is about a dozen services or so. The way we architect our organization is ownership around these service boundaries. And so these 12 microservices are owned independently. I say 12, it's about a dozen. But they're owned independently by what we call two pizza teams. This is a pretty popular concept at Amazon. A two pizza team is a team that reports to a manager that's sized, think of like how many people could two pizzas feed. And that's about what we consider the appropriate size for a team. Having service ownership kind of organized around these two pizza teams allows these teams to move independently. They can own their own operations, and they can own their own decision making. And it's sort of a microcosm of how some of you might have observed AWS organizes at a macro scale. The different services, different products do operate independently. And so it's great for ownership, it's great for operations, but there are some things that we care about that are fundamentally an end-to-end view. Performance is one of our key business objectives. And from a customer's perspective, performance is how you interact with S3. There's no customer that's gonna, if you happen to have performance that you don't like, is gonna be happy if one particular microservice is doing well, right? You care about the whole end-to-end experience. And so the challenge that we face is how do we maintain this end-to-end view that's actually actionable across these teams while preserving this independence that teams have? And so that's what I'm going to talk about today. The first thing I want to talk about, though, before I talk about that, is what is performance? Performance is this term that everyone kind of understands intuitively when they hear it, but if you ask what you actually mean, you get a whole variety of different answers. So we typically hear about performance along three dimensions from customers in S3. One is latency. So latency is the amount of time it takes for, let's say you initiate a GET request, when do you start getting bytes back from the service? That amount of time is what we consider latency. Throughput is sort of what happens after that initial latency. Now that you're getting bytes, how many bytes per second are you actually able to get? The last dimension that customers often talk about is request rates. Independent of latency and throughput, just how many requests per second are you able to submit to the service? And that can be influenced by a variety of factors. Within those three dimensions, there's different ways to look at them as well. So different measurements. The raw magnitude, right? What's the average number of requests? What's the throughput that I tend to see, the latency that I tend to see? But often what comes up is variance on these measurements. So while the magnitude of the performance measurements is important, the variance is actually often more important for customers. And so what we're going to talk about today is variance of latency. That's the kind of objective that we're going to look at. So why does variance and latency matter? It turns out that data lake workloads, analysis workloads, are very sensitive to the slowest requests. So this is a talk about using data analysis, but in S3, of course, we underpin a lot of data analysis too. And So these data lake workloads often we'll submit multiple requests simultaneously, but there's a lot of dependent IOs that occur where you can't initiate a certain part of your analysis until a previous part of your analysis is done. And so if there's variation in the latency, it can really affect how long your jobs take end to end. You might be accustomed to a job taking 2 hours, and then one day that entire job end to end takes 3 hours. One measure that we look at when we look at tail latency internally is this measurement called, we call it P99.9. It's the 99.9th percentile of requests. So it's the slowest 1 in 1,000 requests. This is what we consider like outliers. And our goal is to drive down these outliers. And we have a multifaceted approach to doing this, but one of those facets is performance logging. So I mentioned that we have about a dozen microservices. They're all producing performance logs. And they're introducing timers and really instrumenting requests. And so before we can actually analyze and produce this end-to-end view, we have to take these disparate systems that are producing separate logs and join them. And we produce multiple exabytes of logs internally a year. And so this is a really big data problem in and of itself. So before we talk about our pipeline that's set up to analyze these logs, let's dig into a little bit of where latencies come from. There's a variety of sources of latency, and I'm going to go over some of the common ones here. This is not an exhaustive list. So I mentioned earlier we're comprised of about a dozen microservices on the request path. So those microservices have to communicate with each other. And oftentimes, because those microservices are running on separate machines, there's a network hop involved. In a general sense, when you're talking about deploying to EC2 and you're looking at the latencies between services, there's sort of this spectrum of latencies you can expect. If you have instances within an EC2 placement group, that's going to be your best possible inter-server latency. Aside from that, within an AZ gives you your kind of next best possible latencies. Then you go across AZs. Latencies are going to be a little bit higher. And then when you cross regions, because regions are very physically separated, latency is even higher. As some of you might know, S3 is kind of by definition a regional service. So we're designed to tolerate loss of a facility. And what that means is, by the time you have put data into S3 and you get that acknowledgement, your data is already in multiple availability zones. And how that matters here is that fundamentally, your operations in S3 do require cross-zone hops. And so that's what we've highlighted in yellow here. But there is this kind of fundamental source of latency due to the product definition. The storage media itself that we use is a source of latency. So let's do we're going to go on a little side quest here. So we're going to look at how hard drives work. This animation looking all right? It sure does. So I'm going to go over this in some amount of detail. Don't worry if you're not following all of it. But okay, so this is a simplified view of what a hard drive looks like. And you'll notice here, there's sort of these like two mechanical actions that are occurring. So you can see these platters, these disks on the right, they're spinning, and you can see the spindle in the middle is rotating there. And then you can see this arm, this actuator arm, that has to move back and forth. When you read from a hard drive, you're making a system call, like a read call. You're giving it an address. That address is going to be, the unit is in terms of logical block addresses, but think of it like an offset from 0 to the density of the drive. When you make that sort of request, the drive translates that into a specific location on the platter, on a specific platter. And then a couple of things have to happen. So that actuator arm has to move to the correct location. We would call it a track. And that takes time. Different drives vary, but it takes about 8 milliseconds to get from the outer track to the inner track. And so on average, you have to travel about half that distance. And so it's about 4 milliseconds just to move that arm. And then it's a probability game. Is the data that you're looking for directly underneath that read head at that moment where it lands in the right spot? And half the time, it's going to be close. The other half of the time, you just missed it, and it has to travel around again. And so that the platter itself has to spin back into location so that it's underneath the read head at the time. This is called rotational latency. Some of you might have heard of like hard drive statistics, like 7,200 RPM drives. That's revolutions per minute. That translates to about 120 revolutions per second, which is about 8 milliseconds for a single rotation. And if on average you have to do half a rotation, that's another 4 milliseconds. And so just to do a single I/O on a drive fundamentally introduces some latencies just due to the laws of physics. Okay, so we have hops, we have storage media. Another common source of latency is computational overhead. So we do things with data, right? We're encrypting data, we're encoding data, we're calculating checksums, there's garbage collections in certain stacks. Fun fact here, S3 does about 4 billion checksums a second across the entire service. So there's a lot of computation going on under the hood. A lot of it is just due to our durability culture, and we have very strict architectures around how we handle data. But it takes time. It takes like measurable amounts of time to do some of these computations. The last source I want to talk about today is actually what I consider one of the more interesting ones, which is queuing. So everything I talked about above is about something doing something. So a server has to talk to a server. A CPU core has to do some computation. A hard drive has to go seek for amount of data. Queues are actually about doing nothing. So what I mean by that is these resources that we're using, whether it's a NIC, a CPU core, a hard drive, can't actually do that many things at once. We think of them as massively concurrent, but they can't actually handle that many requests simultaneously. And so when more work arrives than some resource can handle, you sort of have a couple of choices. You either have to drop the work, or you have to reject the work, or you have to put the work in a queue and have it wait its turn to execute. That time spent in the queue introduces latencies. And there's queues everywhere. So when you make a request from a client to a server, there's routers in between. Those routers have queuing. Sometimes if those routers are congested, they'll actually drop, you'll see packet loss, and you'll drop packets out of the queue. NICs have queues. Operating systems have queues. Your applications have queues in the thread pools that you use. Or if you're using synchronization or locking, you're building queues when you have lock contention. Storage media itself does have queues. So queues are everywhere. This is actually why some of you might have seen previous talks where we've given advice for customers of S3 who are looking to improve their performance against S3. And the advice tends to encourage you to spread your traffic around. So at the front door, that means leveraging multiple IP addresses so it spreads around our front end, which, by the way, the SDK would do for you. It means from like a key space perspective to actually spread your traffic across multiple partitions. From a per object perspective, it means reading multiple parts of an object concurrently rather than focusing traffic on fewer parts. These are things the SDK does largely handle for you. But at the core of that advice is to avoid putting too much work on any individual resource, because that's when queues start to build, and that's where latency can come from. So these are some of the sources of latency. There's others. Okay, so we're talking about actually doing data analysis to surface the end-to-end experience to customers. So what I'm going to show you here, this is the end result of what we're actually looking to produce. So what we have here is the stacked area graph, and you can think of the top part of the graph as the customer experience, and the layers subdivide the different constituent components of your request so that individual service teams, whether you're team 1 or team 5, can actually see what their contribution is to these these performance outliers. And this actually serves as this really awesome mechanism for visibility and accountability. And we tend to use this in a couple of ways. So one way we use it, developers can just kind of pull up these graphs and look at them. But what we have found to be really useful is to have, when I say business analyst, I kind of think of a hat versus a specific role. And like sometimes I'll wear a business analyst hat, and sometimes I'm wearing a software engineering hat. But we'll have a business analyst go and actually curate these on a regular basis. And so it starts a conversation because they look at this and they produce these summaries that are just their initial take on what they're looking at. And so it doesn't rely on engineers just happen to pull, like I pulled up this graph and now I want to do something about it. That like proactively starts this conversation. So how do we put this together? Okay, 3 easy steps. So we pull and prepare petabytes of logs from thousands of hosts. We reassemble and measure the latency of trillions of requests based on the performance of these microservices. And then we display the results in a user-friendly way in a completely self-service tool every hour. So this is clearly an oversimplification. Here's what our actual architecture looks like. So we start out with, we have an external log storage service. You can imagine which storage service we probably use to store our own logs. And I'll give you a hint, it's our service. Then every hour, we are taking that log data and we're converting it into a Parquet format and putting it back into another S3 bucket. We're triggering a separate EMR Spark cluster to do analysis steps on that Parquet data. We're storing the results in Dynamo, as well as another Parquet format for Athena queries. And then we have a Lambda backend fronted by an API gateway for a web GUI. And then we have, ultimately, a web application that our developers can pull up and look at. And it allows them to drill into it. It's not just a static graph like what I showed you. It's actually rather dynamic. In terms of the scale of this system, it's about 400 or so M5 12XL servers that are running the EMR Spark cluster. It's about 19,200 cores, and in total, it's 76.8 terabytes of RAM. And so that's what we have deployed to process those petabytes of logs an hour. And it's actually really important that it can process all of those logs in less than an hour. Otherwise, we start building a queue, because these logs are coming in every single hour, right? And if we take more than an hour to process the hour, we either fall behind or we have to increase the cost of the system. This approach has actually been really successful for us. So there's been a number of real improvements that we've been able to make to the service based on our observations here. One of the more interesting ones, which I think is really important to highlight here, is what I'm calling unintended outcomes. So we have this data set that's designed for analyzing latency. Our data scientists were looking at this data set, and they realized it could be used to meet another key business objective that we have, which is to be able to ingest the industry's latest hard drives. And so that seems kind of weird and unrelated, right? I have this latency data set, and somehow I can use it to like ingest hard drives. Like, what does that even mean? So let's take another side quest. If I can get the clicker to work. There we go. It's the picture from earlier. There's our friend, the hard drive again. Hard drives are getting denser. So when S3 launched in 2006, hard drives, the latest, greatest hard drives, were around 250 gigabytes. Today, 20 terabyte drives are available. That's a pretty dramatic increase in storage density. The technology to get us here is actually pretty amazing. We're super excited about these next generation of drives that are coming online. They're called HAMR drives. It's HAMR, which stands for Heat-Assisted Magnetic Recording. There's literally, in these HAMR drives, to get to the density they need to get to, they literally have to put a laser on all of the write heads that are at the end of that actuator to heat up the platter so that it's actually writable. That's the only way they can get as many bits per square inch, is if they make it out of a material that needs to get heated up. The technology here is just, frankly, it's way over my head, but it's phenomenal. So earlier I talked about how hard drives work, right? The platter spins, the actuator moves. Well, back in 2006, when we had 250 gigabyte drives, we were able to get about between 80 and 120 I/O operations done per second. I/O operations per second, IOPS is the typical term you hear. And this number makes a lot of sense in the context of the latency calculations we had just done. Right? If on average a seek and the rotation takes about 8 milliseconds, there's 1,000 milliseconds in a second, there's variation there, and so somewhere between 80 and 120 IOs per second. Today, with 20 terabyte drives, we're looking at the same 80 to 120 IOs per second. So we often like to talk about hard drives in terms of storage density, 250 gigs per drive versus 20 terabytes per drive. But there's another useful density number to look at, and that's called access density. So hard drives are getting denser. The ability to access those drives in terms of IOs per terabyte is what's called the access density. And if you think about, I'll do the math for you ahead of time. With a drive that can do around 80 to 120 IOPS with 250 gigabytes of storage, that's 400 IOPS per terabyte. If that same drive goes to 20 terabytes, but the IOPS stays flat, we get 5 IOs per terabyte. And so that's like an almost 2 order of magnitude reduction in the access density of drives over the years. And so this, combined with the fact that workloads are actually getting hotter, they're getting more active, creates this like really exciting technical challenge for us, right? Because the access densities are going down, meanwhile the access rates are going up. And so it's really important for us to pay really close attention to how we manage I/O. And we sort of have 3 general techniques available to us to manage I/O. So the first thing we can do is increase the supply of I/O. And it's on the surface that sounds like, well, you're just spinning the drive faster or the actuator somehow moving faster. And it's not what I mean. There's a few ways you can effectively increase the supply of I/O. If you think about where the I/O limitations come from, it's about really how much movement is required in order to service that I/O you requested. If you can reduce the amount of movement, then you can actually get more IOs done per unit time. And so some creative ways to get there are to be smart about where you place the data on the platters, and to actually, if you have multiple concurrent IOs destined for the drive, give them all to the drive at once and let the drive schedule, as it's sweeping that head across, schedule kind of IOs along the way, even if they came in a different order. Otherwise, you have to swing that actuator arm back and forth, and you're sort of getting worst possible latency there. So there are some ways to effectively increase the supply of I/O. We can also decrease the demand on I/O. One maybe obvious way to do that is through caching. Right? If we are caching data outside the drive, then the next read of that data doesn't have to talk to the drive. The drive isn't seeing that I/O. Another strategy is changing the way that the drive is, the data is encoded. I could do a whole nother talk on this, but long story short, like you can affect how much I/O you have to do based on how you encode your data. Lastly, a really important lever that we have is to spread our I/O across our system better. So last year during, I think it was Peter's keynote, he talked about how S3 is actually comprised of millions of drives. And as you can imagine, we don't have a perfectly uniform I/O distribution across all those drives. I/O, some drives are actually spending more I/O, or some drives are actually using more I/O than others, right? And so you could have some drives that are saturated and other drives that are relatively quiet. And so the better that we can spread that workload across the fleet, the better we're able to leverage the I/O that we've already acquired. And so this brings us back to this latency data set. And what the data scientists who looked at it realized is that they were able to make these observations on workloads, and they could predict with some amount of accuracy read frequencies and object lifetimes. What these allow us to do, these predictions allow us to do, is make better data placement decisions up front. So if you remember, I talked about our 3 strategies. There's the reduction of demand, the increase of supply, spreading your data better. If we can predict what's going to happen in the future on that data, we can make decisions at data placement time that help us achieve those three outcomes. And doing it proactively versus doing it reactively saves us I/O as well. If we have to reactively move data based on what we've observed, then that itself costs I/O. And so it's a big advantage to be able to do it proactively. And all of this came from a data set that wasn't even designed for looking at I/O analysis. It was a latency data set that another group of people ended up looking at and made these observations. So I think it's pretty cool. So now I'd like to welcome Seishu and Aldi up to the stage, and they're going to talk a bit about how Coupang uses their data analytics pipeline to improve their customer experience. Thank you.
Thanks, Ed. Hello, everyone. My name is Seishu Edinutula. I'm super excited to be here at Reinvent. Before I get started, a quick show of hands. How many of you guys have heard about Coupang? Anyone? Oh, there you go. Not bad. There are a few people out here, right? The tech press calls us the Amazon of South Korea. We would like to think that we are like slightly better in some of the areas. Let me talk a little bit about what we do. We have 18 million users in South Korea. Considering that the population of South Korea is only 52 million, that is essentially most of the households in Korea. We have 9 million members. We have many innovative products. One of the things that we do is something called Dawn Delivery. Order something today, and you will get it at your doorstep the next day before dawn. Frictionless returns. There is literally a box sitting outside your apartment. You don't like something, you go put it into your box, and the returns are taken care of for you, no questions asked, right? We have other interesting services. There is things like Coupang Play, a streaming service. There is Coupang Eats, a food delivery service. I think we have last year we had around 18 billion US dollars in revenue. All of this, I think in part is possible. At least I'm part of the data platform, so I think a lot of this is possible because of the data. We collect a lot of data. We collect data from a variety of sources. We have 32 petabytes in our data lake. We have close to 2 petabytes that we store in our data warehouse. There is 1,300 users who are actively within Coupang who are actively looking at the data, making decisions daily on that. There is 120,000 data processing jobs that are doing all kinds of denormalizations, your aggregations, etc. There is 7.1 million logs per minute that we are capturing. And one of the reasons that we capture all of this data is to ensure we're getting the right customer experience. So one of the things we want to talk about today is what we call as the experimentation platform. Like this is how we use the data to enhance the customer experience. We at right now have close to 800 experiments running on the site. For each experience that we want to make available to our users, we create multiple options. There is there is a choice A, there is a choice B. We actually make that available to our users and then collect the data to determine which of them is the right choices, right? And that all of that is done with a platform called as the experimentation. And to talk about that, I would like to introduce Aldi, who is the leader for the XPC.
Thank you, Seishu. All right. So today I'm going to talk specifically about A/B testing. Is how in Coupang we are doing using the data analytics to improve the customer experience. So before we go there, something quick about Coupang. I think we really strive in making our customer feel, how did I ever live without Coupang? So this is something that is always in our mind. So that's why every single features that we actually want to put into production, we always want to measure how is it going to be affecting our customer experiences, right? So there are a lot of different alternate methods, obviously, but a lot of times, like just the keynote speaker says in the morning, right? Intuition versus data, the data is always better, right? So a lot of expert opinions or historical data or correlations around the data sets does not compare on how we're going to do if we're actually doing A/B testing and then measure the customer impact that way. Okay. So starting with the understanding around the experiment lifecycle. What we think about the experimentation and A/B testing, we're always thinking about in 5 different steps. First part is the design itself, right? This is actually the most important step. So I'll leave it to later. The implementation, right? How we randomize, how do we log, monitor, analyze, and decide. Those are pretty self-explanatory. But the design itself is something that is very important. What is inside the design of the experimentation? It is more about how long do we need to run the tests? Who is the target of the user, right? And then most importantly also, what is your hypothesis? Why do you run this experimentation? What do you think the output going to be? So before we go to the hypothesis, then of course, then you will thinking about, oh, these are probably the success metrics that I want to measure, and these are the supporting metrics that I want to measure. Those are all part of the design. It is important because without the design, then your experiment culture for your team or your company will probably not going to improve. The quality of the experimentation is probably going to go down. By thinking more around the design and understanding more, it forces everybody to think through the experimentation before the experimentation even started. Yeah. So this is the next couple of slides is to show some examples on the experimentation that we run in Coupang. The first one is slightly kind of more obvious because we're introducing a live widget. Whenever the live widget is there, and then we want to know what position we want to put in. So the baseline, obviously, we don't have any live widget at all, and then we have 2 test options, one of them putting on the position 5, the other one is putting on the position number 10. So the goal is very simple because it's improving the revenue, obviously, but then we do want to have different kind of test options so we can see what is the trade-off of the position between the revenue and also the user experience, right? But, and then not all the experimentation though is very obvious or about revenue at all. So that's why the next step, I want to show you guys an experiment also that is done. This one is actually just to introduce a seller name inside the review section. It sounds pretty trivial, but what does it actually do? Is it going to improve the revenue? No, it's not, right? Maybe indirectly later on in the future, but not directly. But what it does, it actually increased the customer trust by putting the seller name. And it also increased the credibility of our seller to be doing better for our customer. And then what we see is very surprising that the experimentation is actually improving number of customers that actually revisit our sites after the first exposure, right? So these are one of the example of the experimentation that not purely about the revenue, but it's also for customer experiences. So the next, I'm going to talk about the A/B testing architecture that we have in Coupang. And then to start with that, I kind of want to take a look at, in the simplistic view, what are the things that we do that we need to do for the experimentation platform. So the concept of the A/B testing is simple, right? So you have a target audience. So you selected the audience during the design. And then you want to split them into multiple groups. So in this simple example, we have 2 groups, A and B, evenly split too, right? And then after you split and then you run your experimentation, you gather all the data, you compare the metrics, and you decide whether you launch it or not. So but if you're thinking about, okay, you have 1,000 different experimentation that's running at the same time, and then maybe you run experimentation with like billions of events a day, and then maybe you're thinking about maybe there's 100 or 500 metrics per experimentation, then things get complicated very, very quick, right? So that's why when we actually design our experimentation platform, we do have to think about the infrastructure very, very carefully. So this is basically the infrastructure of our A/B test platform. So starting with the presentation layer, right? This is where the user, whether it's business analysts or is it engineers, We go there to do configurations, we set up the A/B testing, we're selecting the metrics, we stop, we start, we stop again, we start again, and iterates. All are done in the presentation layer. And then it was all processed into Amazon RDS as a data store. And then from there, for every changes that is made, we have a configuration management. The configuration management is managing all the changes of the configs and then actually push the data set into our SDK. So the SDK will subscribe all these configuration changes. So the moment you're actually making a changes to configuration settings, it will almost instantaneously goes to our SDK. And then the SDK itself, other than just looking into the configuration, it's actually sending the log, the exposure events, then in return will be captured in our Kafka stream, right? And then for all the events that is captured on Kafka stream, we also persist them into S3, Amazon S3. So the purpose of this is that there will be two kind of calculations that is going to be ongoing at all time. Some part of it is in the speed layers, reading directly from different Kafka streams and calculating the metrics. And obviously, these are all the near real-time revenues, informations, the conversions, something that's very, very important for our customer and for Coupang, right? Everything happened on the speed layer and doing it very quickly, near real time. And then, but most of the metrics, the other thousands of metrics are all being calculated within the batch layer, which is the metrics engine itself, reading a lot of different sources from S3s. So all the computation we're running on Spark over EMR. And then after the metrics being computed and all that, we push it back to our RDS. So in the presentation layer, our customer will be able to see what the metrics would look like. Yeah. On the next slide, I'll be kind of want to zoom in a little bit more on the metrics engine and how our batch layer work. Because in addition to the scale that we currently talk about on this architecture diagram, configurability is very, very important, right? So imagine if you have like 1,000 metrics from many different sources, right? It could be any team. It could be search, it could be ads, it could be the shopping experience, it could be play, it could be eats, it could be pay. There's so many different teams. The sources are all different. And then each of the metrics will have a lot of different codes, but you don't want to have like 1,000 different code just to actually running the metrics computations, and it's going to be not easily managed and configurable, right? So then the idea is that we want to have one configurable engine, and then we will have two different components that is input to that computation engine, right? So the first one will be the metric configurator. The metric configurations contains what is the denominator and nominator of your metrics would look like. How the metrics definition is, right? And then the second part of it was the event configuration itself, which contains where is the data located and how is the data being partitioned. And a lot of other information that can glue the metrics, the recipe that we can get from the metric configuration and the data set itself so that our engine will be able to compute. So the next is, want to show like some sort of a result that we have. Remember the experiment that we talked about earlier around the seller name with the review sections, right? So this is one of the results of the revisit days metric. So revisit days here is that the definition was the number of days each of user visit Coupang after their first exposure to the experimentation. So it means that if like, let's say certain users are visiting Coupang like 5 days after that, then for that user is 5. And then we compare it between the control and then the treatment. And then we see the differences. So the solid lines are showing the trend on how the average revisit days for our customer. And we see on day to day, it does have a big impact and it's turning positive all the way throughout the experimentation. The dotted line is actually showing a p-value. It is a measure on whether or not what is the probability that the difference that we see is a noise. So the closer it is to the bottom, which is somewhere closer to the 0, the more statistical significant it is, the more likely we are actually trusting the experimentation to yield the metrics that we wanted. So the next slide, we're gonna be talking a little bit more about the lesson that we learned around the matrix computation. So on the previous result, you see how the day by day, the matrix line is and the solid line, those are actually cumulative results of every day. So what I want to go over today is our lesson learned on how our matrix computations were evolving over time, and then where we started, okay? So first we started with the incremental calculation because that's pretty obvious and more low cost in a way. So we start with computing only what is the previous day cumulative data, and then combine it with today's data to compute the cumulative for today's data. So I will say a lot about cumulative and referring a bunch of days. But the idea is that we use the cumulative of the previous day, and we calculate the today's cumulative with today's data. So only 2 data sets at a time. It's fast. It sounds like it's harmless. But then we found things are not always happen like without any problem at all. So what happened if there is a problem with October 1st, which is 4 days ago? Then what it does is that we have to recompute the cumulative day of October 1st again. We have to calculate the cumulative for October 2nd, and we have to calculate cumulatively for October 3rd. And this has to happen sequentially, right? Because of the format on how we do the incremental calculation, we have to do that sequentially. So imagine if you have 100 days of experiment running, and then the first day is the bad one. Then you have to go all the way on the first one, recalculate the cumulative day by day, and by the time you're done, your customer already so angry, right? So then we think, this is not gonna be scalable. We need to be a bit more fault tolerant. Then we evolve. We're thinking through the solution about calculating non-incrementally. So with the non-incremental calculation, it is definitely fault tolerant. Each of the cumulative day that being calculated will be independent to each other, and we can run it parallelly, and we can scale it easily with Amazon EMR, right? But then, if you run the long experiments and then you have to recalculate on every day, imagine number of calculations that you have to put. You have to put every single day's calculation to compute one single day. And then for every single day, you have to do that, right? Because you always have to compute the cumulative of the today of your data. Then you have to get all the data from 100 days ago, okay, to compute today's cumulative data. So it is expensive, and during the recalculations, then there is a bad data, you have to redo everything for every single day. So you have 100 calculation, and each of the 100 calculation will take 100 days, 99 days, 98 days, and so on. It gets very, very expensive very quickly, right? So the problem here is just then not only expensive because the data set become large, then you have to use bigger instance, then you have to pay more money, and so on and so on and so on. And it just have too many, manual steps that we have to do to do that. So the next slide is I'm going to show you what we do now, right? So given the idea that we want it to be fault tolerant, we want it to be quick. So we come up with an approach that if we do remember when is the last good state of the cumulative, you don't have to go back all the way, right? So then we combine both approaches where we do the incremental calculation and we do the non-incremental calculation, and we combine it into one with a state. So the good thing about this is that, so whenever there is a bad day, like let's say on the October 5th was a bad day, right? Then you look at the cumulative of your October 4th, and you start counting from there. And the rest of them you calculate it parallelly, just like how you do the non-incremental way. So for the cumulative of the 10.9, you're looking into the 10.8, 10.7, 10.6, 10.5, and the previous cumulative of the 10.4 that we know that's already good. You don't have to pull all your data set from the beginning of the test. Right? So but then the good thing is that on the day-to-day, when there is no failures, you'll act like the incremental calculation. So you're only looking into one previous cumulative day with 1 day today, and you only 2 data sets. That's it, right? So with this, we actually breaking the trade-off between the fault tolerant and then the latency that we actually need to do, the simplicity of the calculation. right? These help our customer to get the metrics faster and save the computation costs. So this is it today for the lesson learned and how we use the data analytics to improve our customer experience in Coupang. With that, I'm going to give it back to Seth. Thank you, Seth.
Thank you, Aldi.
Thank you.
Super interesting. So I just want to wrap things up here. One of the things I actually found really interesting preparing for this talk with Seshu and Aldi is these are very separate problem domains that we talked about today. We have e-commerce, we have data storage. Yet there's actually a lot of common themes in how we look at our data. A few of them became pretty obvious as we were preparing for this talk, and I wanted to kind of elevate them here. The first one is plan for resumability, and maybe a better way to phrase that would be plan for failure. So you're going to have data analysis pipelines, and those pipelines are going to have issues, right? The issues could be the pipeline itself. The issue could be something related to data quality. If you don't think about that while you're architecting your systems, as we saw when Aldi was describing here, you could end up in a situation where these failures that are going to be inevitable end up costing you a lot in terms of extra resources for reprocessing and extra time waiting for that reprocessing. And so planning for resumability or planning for failure is kind of a key part of building these data pipelines. Another commonality is if you can, go serverless first. So services like Athena, right? There's a lot of advantages to doing serverless data analysis. You get to avoid managing cluster scaling, patching, fiddling with various configurations. And so if that's something that's feasible, you should definitely do it. And it's also often a great starting point when you have a body of data, you're not really sure what questions you want to ask and you just want to explore it. Doing something that requires a minimal amount of setup can be really advantageous there. Of course, you might not be able to do serverless indefinitely. If you need really strict controls over the timeliness of data processing, for example, I mentioned we have to process all of that data every hour in under an hour for it to be useful. You certainly get more control with something like Spark on EMR, where you can configure exactly what you need, you can size it appropriately. And so there are certainly reasons you might evolve beyond serverless, but certainly at first, going serverless can be pretty powerful. The last one is, when I was, I originally phrased this as start small. And someone gave me the feedback that, really what this is sometimes you find what you're not looking for. And so as I work with other engineers, sometimes I hear people wanting to have the perfect data set or have the perfect set of questions that they want to answer before they take steps to building these pipelines. It's just important that you build something. You're never going to, a priori or ahead of time, find that perfect data set. But once you have something that you can start asking questions against, you're going to get different perspectives on that data that can actually unlock a whole lot of insight that you never even anticipated in the first place. And so getting something going is more important than figuring out what the best possible thing in the universe of options would be. So hope this talk was interesting for folks. I'd like to thank you all for your time. It's really important that you fill out the surveys after these talks, because that helps inform topics for us for future talks. I'm going to spend some time outside after I take all the stuff off. If anyone's got questions, I'll be able to just chat about stuff here or Amazon S3 or any kind of questions you have. Seshu and Aldi, I want to thank you very much for your time today. It's been super fun. Thanks, everyone.